Hi, this is a video on my R package, HAM, which stands for Healthcare Analysis Methods. And this package was primarily written for the times we might want to do causal modeling, or we may want to use techniques or methods that strengthen our observational studies. And although these are primarily written for the use of healthcare interventions, they can be used in a variety of studies. I'm going to use a differences in differences technique, which is commonly used in economics, and but I also do have a section on Cronbach's alpha, which is often used in psychometrics. So, but we find these techniques are very useful in many observational studies, and they were often cited in early publications, such as the book by Shadish, Campbell, and Cook on observational research methods. So let me go ahead and get started. We're looking at my GitHub page. You can find examples here as well as code, and I'm going to kind of just run through that code and add in a couple more examples, and you can read more about what the package is about. And you can see when I click on the hex sticker, you can kind of get an idea of where I'm going with HAM. It's healthcare analysis methods, and we're using them primarily to help strengthen our observational studies. Okay, so let me go to some code, and we're going to run through some examples. I'll first library HAM. It's available through CRAN. It's also available on my my GitHub page, but you can just install the package through R as usual. Okay, so here's the demo. This will also be available in my GitHub page. I'm going to go to the demo repository, and you can find that HAM demo there. Okay, so we'll begin in alphabetical order. We'll start with the alpha function. If you're not familiar with Cronbach's alpha, it's a way to look at scale reliability. And you have, in healthcare, we're probably going to most often look at things like surveys on patient satisfaction. So we have this study that goes out to Medicare. It's called HCAHPS, and it's Medicare's survey that it uses to create a star rating system. That one is probably fairly well covered in terms of the scale items, or the scales based on multiple items. So an example that we might have is we may want to look at our clinic's patient satisfaction rating. We might come up with 5 questions asking about maybe the care we got, our interactions with physicians or nurses, or maybe a combination of all of that. But we have this, in this code we have the alpha function, which is in HAM. We enter in the first argument the names of the items that we want to look at. So we have items 1 through 5, and then for our second argument we enter our data set. So CAS, Cronbach's alpha scale, is available as one of the default data sets in the HAM package. So we'll go ahead and run that, and we get interpretations. That's what this second line is. We can interpret our alpha object. So I'll go ahead and do that. Okay, so on the bottom left we can see that we have returned to us interpretations, and it lists alpha, but we do have interpretations for regressions that are coming up. So the interpretation is your 5-item scale has a Cronbach's alpha of 0.92. This is generally considered as being in the excellent range. So we get some idea of what that alpha score means. We do get the scale mean, so if we use all 5 of those items to create an overall average, the scale mean, we see that it's 3.77, and we have some information on its variation, so we get a standard deviation of 0.67. It's a standard practice when looking at alphas is that we give a score if we deleted an item. So ideally we're going to build scales and survey items that all fit together nicely, but if we say if we add in extra items, say we want a 5-item scale, maybe that is about as many items as we feel comfortable asking our patients, or we think that, or we feel confident that they're going to answer. It's hard to ask too many questions when patients are in the hospital, so we want to have we want to have items that don't exhaust our patients or become too much of a hassle for them to answer. So we have it limited to 5 questions, but we might come up with originally 7 or 8 or even 10 items. And what we can do is find out if we remove specific items, can we get a higher alpha than what we started with. And so we find that in the interpretation that removing item I1 can improve the Cronbach's alpha in a new scale to a higher level than the current alpha based on all items. So if we remove that one item, if we remove item 1, I1, then we actually have, from those 4 items, we get a stronger scale, a higher alpha value. So let's go ahead and remove that one item that can lower, that may have lowered our alpha scale. So let's see what, if we have a scale just based on those 4 items, let's see what that alpha looks like. So we'll run that, show the results. I'm just looking at the raw results right now. I'm not looking at the interpretations. And we see that yes, removing item 1 leaves us with a higher or stronger alpha level. So now it's at 0.93. That's still on the excellent range. You may want to consider just keeping all 5. They may be clinically relevant or of key interest. So, but if there are items that you might want to trim and you feel it's a better scale or a better experience for our patients, then you should feel confident about removing item 1. It'll leave you with the higher Cronbach's alpha scale value. So let's go ahead and scroll down. We see that we do get item statistics, the means and variances and standard deviations for each item. And then we do, as we just covered, we do get scale statistics when each item is deleted. So it's, and then at the bottom we do see that we do get some statistics on our sample. We see that we had 100 rows of data. All 100 had data for each of those 5 items, so we didn't have to exclude any rows. So that's why that excluded row at the bottom has a value of 0. Okay, so that was the alpha function. And now we're going to look at assess. And this is the function that we can use to do various regressions. A professor of mine once said that the bread and butter regression method is linear regression or ordinary least squares. And what he meant by that is this is the one that kind of gives you a lot of flexibility, but also kind of introduces the various regression methods. So it's very helpful. And so the two types of causal modeling that we have options for in the ham package would be with differences in differences and interrupted time series models. And those use linear regression as a technique. What this package can really help with is creating those data sets for you, because that's kind of one of the most time-consuming parts, is just coding everything the way you need to. There are a lot of interactions in here and dummy coding needed for that. So this ham package can really just help make that process a lot smoother, or at least a lot faster. All you'll really need is to enter in the assess function is, besides the variables, you need two so that it can create those data sets for you, and those are a variable that indicates time and a variable that indicates which patients are in the intervention or treatment group and which patients are in the control group. So if you have those two variables, then assess will work for you, and it'll create those data sets for you. And so we'll start with just ordinary least squares regression or linear regression, and we'll cover what options we can use to strengthen our analysis. And we see that in here we have just kind of a standard regression. We're looking at cost as our outcome, and we're going to regress it on month and program. So those are our predictor variables. Our data is HOSPROG, which stands for hospital program, and that's a default data set. And the regression method we're going to use is OLS. The other option is Logistic for now. I will continue to expand ham, so we have OLS and Logistic as our two options for now. Okay, so let's go ahead and run the model. We'll look at the results, and you'll notice it's just the same regression results that we get from the statistics function, or the statistics package that comes in R by default. So nothing really new, but we're going to look at this the line that begins with M1 for model 1, and we're going to run the same model, same outcome and predictors, same data, and we're going to look at top coding and propensity scores. So we can top code, and the reason we'd want to do that is that when we're often looking at cost data, it's usually positively skewed, meaning that there's a tail on the right side. We have most of our values on the lower side, but we do get some of these extreme values. We have patients that may be in the hospital for a year or longer, and so there's usually a strong correlation between your length of stay and your hospital costs. Usually the way hospitals bill is they do it by service, but now we're starting to see it more by the level of care that's been purchased through their health insurance. So and finance departments usually go ahead and assign a daily value, usually a few $1,000s per day stay in the hospital. So there's a strong correlation between length of stay and hospital costs. So if we have patients that are in there for a really long time, we don't have a lot of those patients, but they do run up a really high cost and give you that positive skewed data. So if we look at our hospital cost variable at the 95th percentile, that would give us a hospital stay cost of $17,150. I have an artificial data set, so these aren't actual cost values. I think they're probably a lot higher, but we're going to top code at that 95th percentile, which is $17,150, and we're going to add in propensity scores. We're going to base it off of 3 variables. You can do propensity score models with a lot more variables, but we're just going to use kind of 3 basic standard variables, which would be age, gender, and some sort of health risk that we may have automatically generated in the hospital. Okay, so we'll run that model, and just to show you what the distribution looks like, I'm going to do a histogram on the bottom that we see in the bottom right. This isn't actually the most skewed data that we often see in hospital costs. This is more of a log normal distribution, and so but we still see that tail maybe right about where the cursor is at, between that 15,000 and 20,000 is about where we have top coded at. And but we do see some even a greater positive skew, maybe more like an exponential distribution, where on the low end we have most of our costs, and so what we would do if we had if we didn't top code, then we might get kind of more extreme differences. The purpose for ham is to help give us an idea if a program's working, and so by doing, how we would do that is we'd compare a treatment or an intervention group, and we'd compare that group with a control group. So you're probably already familiar with the issue of outliers in our interpretation of results. Top coding can help with that, so that we don't have, if we have a program that works, we wouldn't want to have something that just provides too big or too great of an impact or effect size with our intervention. We want to give the most accurate results, of course, to begin with, but often our finance department uses that number to calculate projected impact, and they're going to use the mean value, so we don't want to give them an effect size that's too big, because when they calculate return on investment, it's often called net present value. Those values could be too high, and we might end up funding or financing programs that don't have as big of a return as we saw because of outliers in the data. So let's look at the results, and we see that the program in that row, it's a significant difference between the intervention and control group, And I'm sorry, I'm looking at the wrong row. I want to look at the. I forgot to mention I put an interaction between month and program, and that's one way that we can look at the effective program when we have many months of data. We can see that difference in trend for our intervention and control group. So when we look at that, since we have an interaction, we want to look at that interaction effect. So at the bottom row where it reads as month by program, we see there's about a $923 decrease. So that's, if not, it would show it's about, I think without the top coding, it's about 985, 990. So in some programs, you're looking at, you'd multiply that cost by, say, thousands of patients per year. So just being off by about $60 or $70 can lead to projection that's much too high. And if you're in a big healthcare system, then you're probably looking at in a year you might look at cases more like 100,000. So that would be a big calculated difference that would be too high. And so now we can just interpret the results, and that's what that function interpret has. Interpret M1, that's model 1, and for the OLS and logistic models, I call them models just because that's by default that's what they are. And for the differences and interrupted time series models, then I kind of specify that they are DID or ITS, those acronyms for those models. But for our standard linear or ordinary least squares model and our logistic model, I'm just going to refer to that as model. Okay, so now it's interpreted the results for us. Move this up. Okay, so now we have interpretations. Last time we used this, it was for the alpha results, but we can see that we have model returned here, and we have information about the results. We'll begin just at the top. These estimates tell you about the relationship between the independent variables and the dependent variable. These estimates tell the amount of change in outcome scores that would be predicted by a 1 unit increase in the predictor, and that's kind of a standard interpretation that we just a description that we see probably in every textbook that we've looked at that covers regression. And then I go into a little bit more detail. I add the following predictor variables have coefficients significantly different from 0 using an alpha of 0.05. And that's why we're looking at p-values that are less than 0.05. And so these variables that I have listed there, we consider as being statistically significant at the 0.05 level. The variables are month, program, p-score, and that's our propensity score variable. That's how it's returned as the variable p-score. And then we have our month by program interaction. Those are all statistically significant. And then I discuss below that, for every 1 unit increase in these predictor values, top cost, and in the similar to how p-score is returned by the assess function, the assess function also, when we do top coding, it creates a new variable and names it top dot, and then whatever the your outcome is. So our outcome was cost. So the top-coded cost variable is now named top.cost. And it's predicted to increase by the value of the coefficient, holding all other variables constant. The following predictor variables have positive coefficients that increase the predicted value of the outcome. So we see that month and program have positive coefficients. And then below that we see that when we indicate the coefficients that are negative, and those are p-score and month by the month by program interaction. And so that's actually a good thing. That's we want to see that we're going to have lower costs. And length of stay is, if we looked at length of stay, the LOS variable, if we ran this, we'd probably see similar results. So maybe we have programs that help get our patients safely out of the hospital faster. And so in this last paragraph, we have R square, and we have just some general information about that, and we report the R square for this model. And we see that this model has an R square of 0.24. So now we're going to move on to the importance section. So if you're doing program evaluations or intervention studies, we may have a number of predictors. We're probably going to have a number of stakeholders with different interests, and they're going to suggest different things that we should focus on to help improve our outcome, or maybe they're interested in certain hypotheses, or maybe they have a different interest, and with that, different sets of concerns that are reflected as variables in our models. So we would want to, with limited resources, we may only be able to act on a few of those. Maybe we can only act on the top 3 predictors that are the 3 most important variables. And by important, I mean that these are things that these are variables that have the biggest impact, or the that explain the most variation with our outcome. So these are going to be the variables that, if we modify them, or are able to impact those values on our patients, or maybe we're just going to find out that there are certain demographics or patient background variables that seem to have the biggest impact. But we want to identify the things that have the biggest impact on our outcome. So that's what the importance function does. We're going to look at we're going to rank the variables in terms of which of our predictors have the biggest impact on our outcome, which move our outcome values up or down, in other words. So let's go ahead and run this command. And we see that we get a walled test. So we get a chi-square. And I'm using Frank Carroll's definition of his partial chi-square test, or his the values that he calculates for the partial chi-square, which we see here. And so he uses that partial chi-square to help rank the predictors. And so we have the information here, but it's probably a lot easier to just to view that in a simple graph. And I have that here in that row 48 in the code. That's the graph. But you can see that it doesn't come out all the way. We have p-values on the far right that get cut off. So what I'm going to do is add in these parameter values. to help modify the graph. And then those are the top two lines of code that I've highlighted right now. And I'm just going to highlight the bottom two that we see now. Those are the default settings, so it'll bring those graphical parameters back to our default. So I'll go ahead and run this code. Okay, so now we can see the graph much better. We can see the values much better. And we see on the left we have our variable names. And these are variable importance. Anything that's statistically significant or has a p-value less than 0.05 gets highlighted in red. All of these variables turn out to be statistically significant at the 0.05 level, so they're all red. We can see that on the right side when we look at the p-values. And say we're on a committee. This would actually be probably more helpful in the when we're just doing like a traditional linear or logistic regression model. When we have to narrow it down so that's usually the best case for this graph. It may be still interesting when we do our differences in differences or our interrupted time series model. But we see if we're interested in the top three things, and we only have 4 variables, so it's but we see in the top 3 we do have the month by program interaction, and that's our key interest. But suppose we had a traditional regression model, and we just wanted to know which of the things were most important. That can help in that discussion with your stakeholders, because we can then point out which variables give you the biggest bang for your buck, or which are the variables that we should focus on. Month by program, that's a significant interaction that answers our question about the impact that we see and how and what it looks like over time. That interaction between month and the program. So we do see an effect over time. Okay, so let's move on to logistic regression. And we would set up the model in the same way. I'm just going to show you the results, and I'm going to use the MT-CARS dataset. The outcome is whether, I believe VS is whether an engine is a V-shaped or a straight line engine. So just go ahead and run that. We get our regression results. It's just a very simple model, and I wanted to show that we get interpretations as well. So we have the interpret function wrapped around our assess function, and that leaves us with model interpretations. Okay, so now we're going to move on to our differences in differences model. Again, we're going to use the assess function. And what's different with this is that we're going to use a couple of variables, and we're going to use them for what I mentioned earlier, that we're going to want to know we're going to want a variable to indicate what our intervention is. In this data set, program is our variable name to indicate which patients belong in the intervention or control group. And we're going to want some sort of variable that gives us the time, or the intervention time. So we want a variable that indicates who's in our treatment and control group, and then we want to know we'll want to know when that intervention started. So we want to know within these 12 months, when did the intervention start, and knowing both will tell us when our treatment group got their treatment. So those are the only two variables that we really need to add, but we do need to indicate when the treatment began. In this data, it's at the 5th month. For the int.time variable, the variable name is month, and the treatment began at the 5th month. And we have did equals many, and I'm sorry, I'm on the wrong code right now. I'm just going to go back. I'm on the second example. I want to go back up to the first example. But it's the same thing. Our intervention variable is the variable name is program. Our intervention time variable is named month. Treatment begins at the 5th month, and that did 2 equals the argument, the value that we enter in is 2. So this gives us a standard pre and post test. We have a binary time variable, and we indicate that by putting in that argument 2, meaning we have just 2 time points, the pre and post. How it's coded as a 0 or a 1. On that second example, we're going to look at it when we have more than 2 time points. Say we're looking at months and we want to see how that trend looked. Maybe we're expecting that we're going to have a gradual impact or an immediate impact, or maybe something that's incremental. By looking at time as a continuous variable rather than a binary pre and post, it gives us more of an idea on that. But we're going to start first with just that pre and post test, 2 time points, hence did equals 2. So go ahead and run the model. We're going to get a summary of results, and this is the standard differences and differences model. A pre and a post. I believe it was the 2020 or the 2021 Nobel Prize in Economics went to Angrist and Pischke, Imbens, and I think David Kruger. The prize was split between the 3 groups, and they got it for the differences in difference model. And it's often referred to as differences in differences by Angrist and Pischke, but sometimes it's referred to as difference in differences or even difference in difference. But it's the same model. And your key variable of interest would be this did variable that we see in the last row of regression results. And so our outcome is length of stay, and you'll notice that I have just the dot or the period at the end. So I'm just doing a kind of just a basic difference in differences model. So it's going to construct those variables for me. I used program and month in my arguments, but what I get returned is post all int.var and the did variable. Those are constructed by the assess function, and it creates the variables for my model that I need, and so those get added into the model while assess is processing everything. So so a very helpful function is the interpret function that we used earlier. It will work on differences in differences models. So let's go ahead and look at the interpretations. Okay, so we look at the top. The heading is Interpretations DID. Gives us some information about the intercept at the beginning, 3.494. Post all tells us that post all is a change in the control group's length of stay value in the second time period, time 2. There was a significant increase for the control group at time 2, and time 2 is actually, since we're coding time as 0 and 1, it's when that when monthly, or let's see, yeah, in this month is coded as 0 and 1 in this, for this example. So we see that value is 1.626, and int intervention variable, our int.var, is the difference between the intervention and control group at the baseline period. The intervention group had a significant increase in the mean length of stay value compared to the control group. The value is 2.066. And now we're going to look at our key variable, which is the DID, differences in differences estimate, the average treatment effect on the treated group. This interaction represents the difference in the trend differences for the intervention and control group, hence differences in differences. And we can see that if we were to calculate it, we would look at the intervention time 2 minus the intervention group's time 1 value, and then we would subtract the control group's time 2 value minus the control group's time 1 value. And if you do that calculation to get your differences and differences, that would come out to negative 3.57. In other words, there was a significant decrease in the mean length of stay trend by negative 3.57 for the intervention group. And then at the bottom, I just give a general statement that is, if there were additional variables in the model, then the coefficients above represent the effects after controlling for the other variables. Okay, so at the very top, I'm going to go back to the line 70, DM1, and we see that the formula is length of stay defined as the period sign. But if we wanted to add in, say, age or the female indicator, then we can do that here as well. We can replace that period with something else, or a propensity score, and we get results for that. But if you just want to get kind of your standard set of results for those key variables that are part of a differences and differences model, then you would just do the period sign where your variables generally go. And if we wanted to add in other covariates or predictor variables, we can replace that period with those variable names. Okay, so now we're going to graph our results. Okay, so what we're looking at is I'm going to zoom in, and what we're looking at is, let me just fit this to the screen a little bit better. Okay, so we have a differences in differences model. We have, in our legend, we have a line for the intervention in solid blue. In red, we have a line that represents the trend for our control group. And in that dashed blue, we have a counterfactual. We often get asked, well, what would have happened if we didn't have that program? If we didn't have our program to help with length of stay or cost, what kind of trend could our intervention have expected without that program? And so that's what that counterfactual is. And so you can see how it's parallel to that red line, which represents our control group. So hypothetically, we could have seen an increase in length of stay. We're looking at length of stay in this analysis. And what we saw instead with that we have in that blue line is that the length of stay decreased. So had we not had the intervention program, we would have probably seen an increase in length of stay similar to what we saw with the control group. So that dashed blue line gives us our counterfactual and lets us kind of get a better idea of what that that intervention effect is, and that we see that 3.5 day difference is what we would expect, that difference between that dashed blue line and that solid blue line. So that's where we get those values from. But that's how we can graph it. The counterfactual is a common way to help understand our results, and it's part of that plot function for differences in differences. And we have a similar option for some of our interrupted time series models, but kind of a standard way to look at your differences in differences result is to have that counterfactual. So let's go on to the second model. So this time we're using a continuous time variable with time points with more than 2 time points, and we do that with our DID variable. Our DID argument, and we would use many. So again, we're going to use that month variable. It's the same variable that we had in the previous model. And so what in the first model, in the previous model, everything that was before that 5th month got recoded as a 0, and everything that was after that, at or after the 5th month, became a value of 1. In this case, it's not going to recode that. Instead, it's going to use I believe it's 12 months. It'll use the full 12 months. And but we still want to indicate when that treatment began. I used the term many to represent a continuous time variable. So rather than 2 time points, we have many time points. So let's go ahead and run the model. We'll interpret the results. I'm just going to kind of skim through this. But we do have 2 estimates that we want to look at that are of key interest. The one is DID. That would indicate it estimates the average treatment effect on the treated group. This represents the difference in the mean overall level between the intervention and control groups. In other words, there was a non-significant increase in the mean length of stay by 0.101 for the intervention group. And then we have the trend. So the DID part represents that immediate shift after the intervention started. And that's the DID estimate. But we may want to know what that trend looks like after the intervention is gone. So we know that we have 7 other months after the intervention began. And so we want to know, well, does that trend remain flat? Does it keep going? Do we keep seeing progress? Does that impact happen but briefly and then goes back to the way we'd expect it to go, as we see with the control group? So that DID trend, which I'm highlighting now, represents that. So we can see what the trend looks like after the intervention has been going for a while. So DID trend is the difference in the intervention group's trend line after the intervention period started. The intervention group had a significant decrease in trend of the mean length of stay by negative 0.193 after the intervention started. So month after month, we see that length of stay go by about a fifth of a day, or about 0.193. So that's with that DID trend. We have two variables to look at, and let me just, I'm going to bring that up. I'm going to show you those results directly. Okay, so this is for the second model. Okay, so in the actual results, we're looking at those last two rows. So there wasn't a strong immediate shift, but instead we're seeing that length of stay decreases month after month for our intervention group. Okay, so and a common best practice for differences in differences model when we have binary outcomes is to continue to use our linear regression model. I think there have been some improvements in using logistic regression for that, but there has also been some inaccurate or unclear results when using logistic regression. So it's and oftentimes we're looking at aggregated data, maybe year after year. So we may, one of the benefits of differences in differences that you can use this on aggregated data, but one of the better practices when you have a binary outcome is to actually use linear regression, because we may just be interested in that big overall trend. So we can use differences in differences for a binary outcome. That's what has been considered the better practice the last few years, but I'd recommend looking at the literature to see if there have been any improved methods that provide stable and consistent results. But a good option is still using linear regression on a binary outcome for the differences in differences model. So, but I'd still say take a look at the literature to see what's current. Okay, so we're going to look at our binary outcome. I'm going to run the model. We're going to look at 30-day readmission. Same type of model, but just a different outcome. And I just want to show you, yes, you do get results for that. These results are in similar to any type of any of the other models we've looked at so far. Okay, now we're going to go to interrupted time series, and again we're going to specify an intervention. It's going to be program, and we're going to look at the program month. The month variable to indicate time. We have a new argument that we're going to use, and it's interrupt. So these are interruptions. Similar to the DID treatment, we're going to have an interruption at the 5th month. And for the ITS argument, we're going to use one, meaning that we have one single group. One of the advantages of the interrupted time series is that if we don't have a control group, if you're in a hospital system where decisions made system-wide, then you may not have the option of having a control group. Like the Shadish, Campbell, and Cook book discusses, we can't always randomize our sample like a randomized clinical trial. In healthcare, we can't do it often because it could be impractical or unethical not to provide these programs to our patients. If we know we have a program that works, it may be considered unethical to not enroll all our patients in these kind of programs, and it can also be impractical. It would be a difficult thing to randomize when you don't exactly know who's coming in that day. Not to mention that our clinical staff, especially nurses, may have limited time with each patient, so we wouldn't want to burden them with that extra task of randomizing our patients for us. So we don't always have a control group, and interrupted time series models are really good for that purpose when we want to look at the impact, but we don't have a control group to help understand that more. So we're going to run that first model. We're going to look at our results. We have 3 variables in this. So I'm looking at, in this model, I have a single group and I have a single time period. And so these are the 3 variables that I get from that analysis. I'm going to go ahead and interpret the results. Just like our other analyses, we see our heading describes that we're looking at interpretations for an ITS model, an interrupted time series model. And then we have information on each of our different predictor variables. We have an intercept. We have a set of 3 constructed variables. Again, the assess function will do all the dummy coding and recoding of our variables to give us the variables that we need in the model. So this is, since it's one group at one time point or one interruption, we only have 3 variables here, but when we'll see in our model with 2 time points and 2 groups, then we're going to have 11 variables constructed for us. So that's going to really save a lot more time for us. But we're going to see that we have our coefficients, our interpretations, and we do have a summary at the bottom. And this gives us an idea of about how many are the change in the outcome over that period of time. And so we see that and an important thing to point out is that we don't have that pre and post time point, or those pre and post time points, those binary values for time. We're looking at many months. So a key interest that we would have is, what does the change in our outcome look like over that full period of time? And we can see that in our summary. The results show that after the start of the intervention, there was a non-significant change in the length of stay trend. This gives a total post-intervention trend in the length of stay of negative 0.074 over time. In other words, the total combined value of the change, not the change relative to the pre-intervention. And so what that means is that we had a decrease of 0.074 days per month. So each month we were decreasing our length of stay by an additional 0.074 days. So we saw continual continual decrease, not a lot, but that may be an acceptable improvement for our hospitals. But we see a decrease, an additional decrease of 0.074 days for each month that our hospitals in the program. Okay, so let me just move on to the next result. So we want to graph it as well. So we're going to run the plot command. We just looked at the interpretations, but now we're going to look at the plot command. Okay, so I'm going to zoom in. And because we can have different types of trends of improvement, we can see that maybe we're entering in an especially difficult change in healthcare, or maybe with our hospital operations proceed. We may have seen an improvement in our trend right away, and that's what it looks like here. So that solid blue line represents the intervention, the dashed blue line represents the counterfactual. So maybe what the trend could have looked like would have been what we see with that dashed blue line, and that the second part of that solid blue line represents what happened after the intervention. So our treatment or our interruption happened at month 5. So that's what we see that dash is. So rather than having one solid line, with the interrupted time series model, we can see how we can break up that trend line into segments, and we can see that there. It didn't look like it had improved too much by the end of that 12th month, but if this was a period where we knew we were going into a particularly tough period, maybe that counterfactual may not represent what our expected progress would have looked like. But what also could have happened is that we made an improvement, but maybe we went back to our old practices that weren't as helpful. So we have an improvement where that gray dashed vertical line appears, meaning that length of stay decreased, but kind of just stayed there. It didn't continually improve month to month. It was only 0.074, so that's not a big improvement month to month. Maybe we're going to be happy at that 12th month, because maybe we weren't expecting to get that kind of progress continually. But this gives us paints a different picture for us and gives us a better understanding of how progress looked like over time. And so that blue dashed line again is our counterfactual, and we can see what happened and how it happened. We saw a bigger improvement right at the beginning and a gradual improvement over time. Maybe that's what we were hoping for, but we can also use this to figure out how to improve that, if that's what we'd like. Okay, so now we're going to go to the two-group model. Or I'm sorry, that should be it's one group, two periods. Just going to change that right now. Okay, so again, we just have our intervention group. I am using the data set HOSP1. I did that for the previous model, just wanted to mention that. ITS is still 1 because we're just looking at our intervention group, and now we're going to look at two periods, the 5th and 9th month. Maybe there was a maybe we had a health program plus that came out in the 9th month. Maybe there was a full implementation at the 9th month, but we can look at those 2 periods and compare. So we run the model, we look at our results. Okay, let me run the model again. That should have... Okay, I see. I have in the old code from the previous model. So let me get the summary of results again. Okay, so on this we see we now have 5 rows of results. We have post 5, meaning for the that variable for the 5th month, txp5, that variable for the 5th month, post 9, that repeated variable for the 9th month, and txp9, that repeated variable for the 9th month. Okay, so we're going to interpret the results. We get the interpretations here. Summary 1 would represent, well, let me graph it first just so you can see it. Okay, so we have, now we're looking at that trend over the year, but now we're breaking it up into 3 segments. And we can see that there actually was quite a difference between the trends, the trend right before the first intervention, the trend after the first intervention, and the trend after the second intervention starting at month 9. And we can see that we have a big change right away, but it doesn't seem to persist. So maybe in fact what we're doing is when we have that second implementation, when we called it the Health Program Plus, maybe that is not an effective modification to our program, or maybe it's too much of a burden on our health staff. Maybe our physicians and nurses are maybe they didn't have enough time to adapt to the new program, or maybe we're just not properly staffed, but we're seeing a different type of result. So let's go back to the interpretations. For that summary 1, which represents that middle part of the graph on the bottom right, I'm just going to zoom in real quick so you can take a look. We have the segment on the left, which is our pre-intervention period. We have the section in the middle, which represents our first intervention, and then we have the section on the right that represents our second intervention. And the segments are broken up by those dashed gray vertical lines. So let's take a look at the interpretations. We see that for that summary 1, that represents that middle segment of the graph. The results show that after the start of the first intervention, there was a non-significant change in the length of stay trend. This gives a total post-first intervention trend in the length of stay of 0.003 over time. So that 0.003 represents the change in our outcome month after month. So it's tiny, it's 0.003. And the results in the second summary, the results show that after the start of the second intervention, there is a non-significant change in that length of stay trend. That's the section on the right we're looking at. This gives a total second intervention trend in the length of stay of 0.233. So we're actually increasing, and we see that on the right. We see that solid blue line going up over time. So we may have a big impact right when we started programs, but it doesn't seem to hold. So we may need to discuss with our leaders and our performance improvement teams the type of improvement we're seeing, but the fact that it's not lasting should concern them. So that gives us a really a much more detailed review of this data. If we hadn't looked at it this way, we'd get a different picture. So we do benefit by looking at our research question this way, and also gives us an opportunity to figure out how to improve that trend. Okay, so these are kind of more complex situations that we would come across. So what I wanted to do was show one of the reasons I wanted to make the ham package is because since COVID, we've been asked to look at similar outcomes or a variety of outcomes, and we're asked, how does it look post-COVID? Or we might get asked, are we getting back to normal? Or we may not even get those questions. We may just, our hospitals may ask, what's our trend look like? Forgetting that we were in a really tough, chaotic time with COVID. So having these types of analyses can help us present and describe the kind of change we had due to those due to COVID-19. So we can answer what normal is, but we can also address that COVID had an impact on these outcomes, and our clinical staff are doing their best. But we need to keep in mind that we're looking at a trend now that's coming from a different place than it did before COVID. So the data I'm looking at here is a public domain data set, and I have the link here, and it's the inpatient bed use throughout the U.S., the number of beds used before COVID, during that first 8 months after the lockdown, and then we have about a year, I think it's about 20 months of data after, about 19 or 20 months after the COVID vaccine was introduced. So we're going to look at the trend before COVID, during COVID when there was no vaccine, and then the months after the vaccine. And we're going to look at that trend of inpatient bed use and how it compared, or how it looked across our 50 states. Okay, just because, just to show kind of this trend and what a study might look like, I made California the intervention or our exposure group, because it was a particularly tough or high number of cases in California compared to the rest of the country. The South and Southwest also were hit hard, particularly hard in the later months, but New York was hit the hardest, the soonest, and then they brought, and their rates came down, but California was also had a very high rate and a high number of cases that began a few months later. So we're going to make California an exposure group just so we can compare California with the other 49 states. So I'm going to recode that here, and I have that CTCA. That's if we wanted to do these two single group models where we're just looking at California, we can do that with that CTCA data set. But we're going to start with the one group. I'm sorry, two group, one interruption period. So that's the IM21 model. So we'll run that code. We'll look at the results. And so in this model, we have two groups. We have our exposure group and our control group. California is our exposure, or it's in the graph it's going to read as our intervention group. But we're going to compare that with our control group, which would be all 49 states, remaining states. We ran the model. I ran this command on line 128, which is to interpret our results. So I'm going to scroll up really quick. So we see that we have that interpretations heading for our ITS model. And then I just have on the top note that variable names below are based on time points or interruptions. They won't match identically with the output. So if I have time 1, so if our intervention happened at 12 months, the 12th month of our study, it would be considered time 1. This analysis is for a two-group intervention period. We have positive values indicate higher intervention group values and vice versa for these variables. And so we have information on our intercept. And then our other variables. One of probably our two most important variables would be txip1. This is the trend that we see after the intervention. And then our second variable of interest would be IXP1. And it's the difference between the intervention and control group in the period immediately after the intervention started. So when we were looking at the difference in differences model, it would be that shift right away. And that TXIP1 would be that trend after the intervention started. So we have IXP1, which would be our immediate change, and TXIP1, which would be that trend after the intervention started. So combining those two gives us an idea of what that kind of impact and trend look like. In our summary, we see that for the intervention period, the results show that the intervention group's significant shift in the inpatient beds used post-intervention was 447. The control group's non-significant shift in the patient beds used post-intervention was 96.287. The significant difference between both groups is 351. So for the intervention, which would be California, bed use increased about 450 beds per month. So it kept going up an extra 450 per month. While in the rest of the country it was about 100 beds. So it's about the trend was about this 4 times higher after COVID started. Okay, so it would really help to see the graphs on these, so I'm going to do that. Just it'll make a lot more sense. I do have something called itsEffects in this line, and I'll cover that more in the next model. Let's just go right to the graph. Okay, I'm going to zoom in on this. Okay, so we see that dashed vertical gray line that represents when the interruption happened. This would be April. It would be the first full month of the lockdown in 2020. So we see before that our trend between California which is in blue, and red we have the trend for the remaining 49 states. It's about the same. There weren't, each hospital is probably spread according to, it's probably planned to get located in areas where you have a certain population that needs healthcare or health services. So they're spread out across most of the country, and we probably have a hospital roughly what they call a catchment of a certain area that covers what you'd expect a hospital to be able to service or care for. So we see about the same number of beds being used in California as the rest of the country. And then when that dash vertical line represents April. So we started to see a lot more COVID cases. And you see that big jump in hospital beds used, or inpatient beds used in California. And it looks like that trend is a little bit higher for California. It's looks higher. So in April, that the number of beds being used jumped up a lot, continued in increase. It did jump up a lot for the rest of the country, and we see that in that red line around that 4th month. And their trend seems to be increasing slightly as well. So California saw a lot of cases, and they continue to increase, but so did the rest of the country. So there's a big immediate effect. The trend after April, both increase, and California appeared to increase a little bit more. So we're just looking at one interruption starting in April, and it goes for the next 28 months. It goes out to about 32 in this graph, 32 months after January 2020. It's about 2 years, 8 months altogether. So let me close that. Okay, so that's what the trend looks like. If we just create a segment between the first 4 months of January and the next 28 months after that. So let's run our next model. And we see we have 2 groups and 2 interruptions. And so the first interruption is at the 4th month, which would be April 2020. And we got the vaccine, I believe, in January. I think the first doses were given out in January of 2021. We have 2 groups, California and the rest of the country. I put in the argument for new data equals true. So I want to get the data back. If you prefer using another stat software, you can still use the ham function to produce the data that you can use, give you all the variables that you're going to have, and you can use this with another software if you want. You just put new data equals true so that you can get your data returned back to you with all those new constructed variables. Run the model. We're going to look at the results. Okay, so now we have our intercept at the top, of course, and then we have 11 other coefficients for our 11 constructed variables. Okay. And now we're going to interpret the results. I'll run that command for interpret. And we have those key variables as well as an interpretation of all our variables. Remember, we want to look at the IXP and the TXIP variables. At that 4th month, it's going to be IXP1 and TXIP1. And then at the variables that indicate the intervention or the COVID vaccine, or when we began that would be IXP2 and TXIP2. So you can see how things look differently after January 2021. So those are our key variables of interest, but we also want to look at the these different effects for those 2 different time periods, or those 2 segments, summary 1, summary 2. And those represent when our first and second interruptions happened. Okay, so again, I think it'd probably be, we can come back to this, but it would probably be a little bit easier to look at the graph for that. Okay, so let's zoom in on that. I ran the plot command for our model results. Okay, so what we do see is that, again, before we had our COVID lockdown, the trend for the number of inpatient beds used in hospitals in California and the rest of the country were about the same. We see that the blue line for California, the red line for the rest of the country, those trends are pretty similar. California does have a slightly higher bed use, but the trends look very similar. After the COVID lockdown began on the 4th month in April 2020, we saw a big shift in the number of beds used, more so for California. And then if we were to look in that period, we see that now we see a steeper increase in bed use in California. We see that with that solid blue line. There was an increase in the rest of the country as well, but that looked a lot bigger for what we saw in California. After January 2021, we see even or very, very similar trends for both California and the other 49 states. We see that trend level off. So, probably, of course, in addition to a vaccine, we also, as a country, we were treating and providing care for patients with COVID as well as other diseases that were happening at the same time, we saw a better shift or trend of care. So it's not just going to be the vaccine, but how we responded to COVID across the country improved. So we see that level trend in bed use, probably moving patients around better, also providing for care in the home. So we may have, in those first 8 months, we may have kind of not maxed out on the number of beds we had, but we were, for a lot of places, they were almost at their limits of the number of beds we saw being used. But overall, this graph shows us what the trends look like before April 2020, but in the remaining 8 months of 2020 that we see in that middle segment. And then on the right, we see from January 2021 on for the next couple years. So if you use an interrupted time series, you get a better look at that trend over a period where you might have different things happening at the same time. We have COVID happening, but we also have our response to it. So now we can get a better idea of what those trends look like. Okay, so I'm going to first, so we do get, I have a data set called beds. I'm just running all this code right now, but beds is the data set that I've made based off of the new data that I requested from the last model we ran. And the reason I did that is that I may want to use this data with a different statistical software or a different package. The one package I recommend above all else would be Frank Carroll's at Vanderbilt, his RMS package. It's an incredible statistical software package. Just has helped me in numerous ways over the years. But he has the S in RMS stands for strategies, and he has great strategies on how to analyze your data. And one of the things he has in his RMS package is generalized least squares. It's like ordinary least squares, but helps us to count for groupings or clustering. And so one of the things that we sometimes need to do with interrupted time series analysis is that we need to account for autocorrelation, and that just means that if we're looking at California or Vermont or New York, we might have certain things that are different between our states, common within a state. The number of beds that we have in each state is probably limited to a certain number per state. You know, if you're Rhode Island, you might have a smaller number of beds available than, say, New York or Texas or Florida. So we might have trends that are unique or consistent over time, and to control for that consistency, we need to control for something called autocorrelation. And Frank Carroll's RMS package has the GLS regression method, generalized least squares, and so that helps with autocorrelation. That's one of the things that we need to account for with certain type of data when doing interrupted time series. So you can do the same analysis I have all these different variables that I pulled from my new data from when I ran the data with the ham package, and I specify a correlation structure, and I say that, and I specify that we're looking at that correlation structure as month defined by state. So I ran that model. It gives us one of the things about if you don't adjust for autocorrelation, it can give you standard errors that are too small. So if you have a standard error that's too small, when you calculate your p-values, they also look too small. And so what that means is we can have results that look significant, but are in fact a result of or side effect of autocorrelation. And so we don't want to present significant results when we don't actually have significant results. So I'm going to show the results for the GLS22 model that I just ran. So these are pretty similar to the intercepts, about the only big difference, but the effects for each of these variables are close, but probably more accurate with the GLS function. So if you want to control for autocorrelation, you can run the model with the GLS function in the RMS package, and you can get the interpretations and just substitute those values for what you have in your GLS output. The one thing that is going to be different would be the effect sizes. So I have a function called itsEffect. So I'm going to run it right now, and that gives us the what's in the interpretations under summary. That comes from the itsEffect, so that the results we're looking at here get sent over to the interpretations and are in that. Let me just show you one of the interpretations really quickly. Okay, so that one part that reads as summary at the beginning, that would be that section comes from the itsEffects. So you can redo the model, substitute in the coefficient values to get your interpretation, but the one thing that you'd have to additional thing you would need to modify is those interrupted time series effects that go in the summary. So you can do that, but my itsEffect function will do that for the RMS package's GLS function. So again, I'm going to run the itsEffect for the model we just ran with ham. And when you do that, you want to specify the type of model. It's in the documentation, but MGMT means multiple group, multiple time. So you just specify that there. It's in the documentation on how to do that. And then you can do the same thing for the GLS model, which we have in that bottom line. GLS22 is that GLS model. And then I run the same value. We do get similar results for the first time period, but we do get slightly different results for the second, for the effects in the after the second interruption, which would go in summary too. So the numbers are different, but that's probably because these aren't strong effects. You can see in the p-values in those last three rows. P-values are large, so it's not too surprising that our effects vary quite a bit. When we have a really low p-value, these effects on the top 3 rows are very similar. So it's not a surprise that our non-significant effects in those bottom 3 rows vary. So in this case, we can understand why those values are different. In the future, if you do use this and you use the GLS function in the RMS package, you can deal with autocorrelation, create that model, and then bring it over into the ham itsEffect to give you the accurate effect sizes. Okay, so that's it. I hope the ham package is useful to the work you're doing. I will put in my GitHub page. If you have suggestions or spot issues, you can list them there, and I'll get back to you as soon as I can. But I hope this has been helpful, and I hope this ham package will help for any of the work you're doing. So thank you.